In this lesson, I will talk about the integral of exponential function. In my previous videos, I had already shown to you how to get the antiderivative of the natural exponential function. It's quite easy. But this time we shall look into the integral of the general exponential function. So what do we know about the natural exponential function in relation to the derivative? And so again, we have to go back to the derivative because the integral is the antiderivative. We know that the derivative of e to the x with respect to x is e to the x. This implies that the integral of e to the x dx is equal to e to the x plus c. This is just the immediate consequence of our understanding of the integral. It's the antiderivative, okay? How about the derivative of the general exponential function, okay? A general exponential function is a function like a to the x, where a is a positive real number, not equal to 1, okay? When we have something like that, the derivative of that with respect to x is a to the x times ln of a. And this is in fact the generalization of our derivatives for exponential functions in general. Okay, we can apply this to your natural exponential function. So the derivative of e to the x, okay, with respect to x is equal to e to the x times ln of e. But you know that ln of e is equal to 1. So this is just e to the x. So from this equation, we can now write a to the x is equal to 1 over ln of a times the derivative of a to the x with respect to x. So what then is the integral of a to the x dx? Well, it's equal to the integral of this. Okay? So 1 over ln of a is a constant. We can move it outside the integral sign. And so this becomes the integral of a to the x dx is equal to the integral of this dx. 1 over ln of a is a constant. We move it outside the integral, and the integral of this with respect to x is just a to the x. Again, this is the immediate consequence of the fundamental theorem of calculus. Let us find the integral of e to the 2x dx. What is that function so that when you get the derivative of that function with respect to x, it will give you this? Okay? Well, it can't be e to the x, okay? It can't be e to the x because the derivative of e to the x with respect to x, okay, using your chain rule, this is e to the 2x times 2. But this one is e to the 2x. This one is not e to the 2x times 2, okay? So this one requires substitution. So in my recent video, I spoke about substitution. I hope that you saw it. And if you have not seen it, I think it's going to be difficult for you to follow what I'm doing now. So this is my solution. So I will use substitution and later use we know about the integral of exponential functions. Okay, so let u be equal to 2 times x. Du is equal to 2 times dx. And from here, okay, you can write dx as du over 2. So we are using substitution. We cannot go straight into getting the antiderivative of an exponential function. Okay, so we are first using the substitution method. And this is what's going to happen next, okay? We can now write this, the integral of e to the 2x dx, we can write it as, this one is e to the u. the integral of e to the u, and then dx, we will replace it by du over 2. Okay, so 1/2, we can write it outside the integral sign. And the integral of e to the u du is just e to the u. And so, the integral of e to the 2x dx is equal to this, 1/2 times e to the 2x plus c. If you want to check if you got the correct answer, all you have to do is get the derivative of this result, okay, with respect to x. And what is this equal to? So 1/2 is a constant coefficient. You just copy it. The derivative of e to the 2x is e to the 2x times 2. 2 divided by 2 is 1. So this leaves you with e to the 2x. And that is precisely what we are integrating with respect to x. Obtain the integral of x times e to the x squared dx. So this one again, you cannot go straight into getting the integral of an exponential function. It won't do. There is an intervening step, and that is substitution. So let u be equal to x squared, du is equal to 2 times x dx. Now, look at this. You know what? The name of that technique is substitution. Okay, that is telling you what you must do. You will look for a replacement for these functions and for these expressions. So you will look for an expression for dx, x times dx. Okay, so from here, look at this. Du is equal to 2 times x dx. X dx can be written as du over 2. So what's going to happen now is this one will become e to the u, and then this one, x dx, will just be simply du over 2. Now there you have it, okay? The integral of x times e raised to x squared dx after substitution is just equal to this. And that is now easy to integrate, okay? We move out 1/2 outside the integral sign. The integral of e to the u du is just e to the u. And so this is equal to 1/2 times e to the x squared plus c. Now, do you want to check? Do you want to check if your answer is correct? All you have to do is get the derivative of 1/2 times e to the x squared, okay? Derivative of that with respect to x. Again, chain rule, 1/2 times e to the x squared times 2x. 2 divided by 2 is 1. And so this is x times e raised to x squared. Okay, and look at that, look at that. Okay, look at that. Now, let us get the integral of this function. The integral of cosine of x times 2 raised to sine of x dx. So I hope that by now, you can now see the appropriate substitution to do. You know what, for most newbie students who are new into integration and new into substitution, sometimes they cannot see right away what is the appropriate substitution to do. But I hope after examples, after the examples that I had shown, you can now see that the appropriate substitution to do is this. Let u be equal to sine of x, and so du is cosine of x. Now look at that. Okay? Du is cosine of x dx. So you will just replace that by du. And this one will become 2 raised to u. Okay? So the integral of 2 to the u du is equal to 1 over ln of 2. Okay, I know it's not easy to remember that. I can remember my days when I was your age. Okay, it's easy when the function is the natural exponential function e to the x. But when the base is something else, yeah, it's not easy to recall it. Okay, So it's going to be 1 over ln of 2 times 2 raised to u. And then you just bring back the value for u. So this is the result. Again, do you want to check it? Okay, so if you get the derivative of this with respect to x, that should bring you back to this one. Let us get the derivative of 1 over ln of 2 times 2 raised to sine of x. Okay? So this is a coefficient, a constant coefficient. You just copy it, ln of 2. You apply chain rule. The derivative of this is 2 times ln, 2 times raised to sine of x times ln of 2 times the derivative of sine is cosine. Yeah, cosine of x. Okay, ln of 2 divided by ln of 2 is 1. And so this gives you cosine of x times 2 raised to sine of x. And look at that. So that's the way to check. Obtain the integral of ln of 2 raised to cosine of x dx. Okay. I hope that you can recall from your what? This is maybe part of junior high school math. No, senior high school math, general mathematics. You know, the logarithms, the natural logarithms. Okay, ln of 2 and 2 is raised to cosine of x. That is just the same as cosine of x times ln of 2. Okay, that is among the properties of your logarithms. What does that mean? So ln of 2 is a constant. You can move it outside the integral sign. And so it becomes ln of 2 times the integral of cosine of x dx. And you know the integral of cosine of x dx by now. You should know it now by heart. It's one of the easiest antiderivatives to get. It's equal now to ln of 2 times sine of x plus c. And by the way, you can also write this as sine of x times ln of 2. And using the properties of your logarithms, this is ln of 2 raised to sine of x. Okay, so if you want to check if you got the correct integral, if you got the correct antiderivative, get the derivative of this with respect to x. Okay? And it should give you ln of 2 raised to cosine of x. How about this? You know what? This is one of the functions that appear frequently in many disciplines. In stats, in demography, you know, the study of populations, even in the study of the populations of bacteria, this function, 1 minus 1 over e to the x, appear frequently. And you know what, just 3 months ago, I did my comprehensive exam in my PhD. I passed it and I saw this. Not in math, not in differential calculus, not in calculus, but in statistics. I saw this, okay, and I think I got it right, okay? Okay, let us get the integral of this function. Okay, I chose this because, believe me, we are going to return to this one more time when we go to definite integral. Okay, so the integral of 1 minus 1 over e to the x dx, we can apply our linear property of the integrals. That is just equal to the integral of 1 times dx minus the integral of e raised to negative x dx. Where did the negative x come from? It came from this, you know, definition of exponents. It's easy to get the integral of that because you know that that is just equal to x, okay? Now, what is the integral of e to the negative x dx? Well, we can do again the substitution. Let u be equal to negative x. Du is equal to negative dx. So we will replace dx by negative du, and we will replace this by e to the u. Okay, the integral of e to the u, okay, and then negative du, you will just bring out the negative 1 there. So it becomes the integral of, it's equal to negative e to the u plus c, or negative e to the negative x plus c. Okay, so we will put these things together. It becomes equal to this. It is equal to x minus negative e to the x plus c, or x plus e to the negative x plus c. These things are confusing. You know what? Minus the negative. And you will see this again, a lot again. You will see this again when we go to definite integrals.